Hi everyone and welcome to video number 11 of this series in which we are learning how to model an end plate steel connection, which is this model that you see here. In the previous video, we have analyzed some of the files that were generated when we solved this model using Abaqus. So we have analyzed the .sta file, .msg file, and .inp file. Now we are going to finally start the post-processing procedure. Before we do that, let me show you one thing. I have the model opened here, right? If we have something opened in ANSA and we want to empty the database, we can click on File and New, and then Discard, and then we're going to have an empty ANSA session. You see, the database is empty. We have only this empty ANSA part or untitled, that is untitled, and 3 working planes. So this is an empty ANSA section. And now I can get, for example, the .ANSA file and drag it to this position, and then I'm going to end up opening the model again. But that's not what I wanted to show to you. What I want to show to you is that we can open this model by using the .inp file. So we can do this by simply left clicking and holding and then dragging it to this position. Or we could get the path to this folder, Control C, and then go to File, Input, Abaqus, and then paste the path here, press Enter, and then here we have the .inp file. And then I can double click here, and then we have these. In the model action, I usually select overwrite unless I want to merge with another model that is opened. So overwrite, and then you don't need to set up anything here. Obviously, that depending on the situation, if you want to merge to models, then you're going to select merge here, and then you need to set up some things here that are important. But I'm not going to show this right now. So let me just put overwrite and click on OK. And then the model is opened. And since we have saved or actually outputted this .inp file with ANSA comments, we have here the model browser organized as we have organized it before. Okay. If we outputted the .inp file without ANSA comments, then we wouldn't have the model browser and some other ANSA related entities organized in this manner. Okay, because for example, the model browser and ANSA parts is something related to ANSA. It's not an information that Abaqus reads. It's not compatible to Abaqus. Anyways, this is just a curiosity that is important. Now, let's start the post-processing. To post-process the results, we are going to use a different software. It is a specific software that is used for post-processing, not only Abaqus results, but we can post-process results from many different solvers. The software is this one, MetaPost. It is developed by BetaCai as well, just like ANSA. So ANSA and Meta are developed by the same company, BetaCai. And then I'm going to, I have version 23 here. You can have any version in your computer. Just don't have version 25 because it's considerably different. So you can have 24, 23, 22, 21, etc. I'm going to open. And then we have the launcher here. I'm going to use the default layout, but you see that we have other kinds of layouts. To be honest, I've never used any other kind of layout. I always choose default, or we can create our own layout. And this is something that companies do. Companies create their own layout with some customizations. Anyways, select default and then click on OK. And then Meta Post Processor is going to start. Guys, what I'm going to say here is very important. For you to be able to post-process results from Abaqus, that is, for you to be able to input the .odb file here in Meta, you should have a Abaqus library installed in your Meta installation. Okay, you're going to see that if you don't have these, when you try to input the .odb file, you're going to get an error here in this position of the screen. Okay, so this is something that you should have installed. And this is something that I can't help you installing. Okay, so if you're using, for example, the ANSA from your company that you work or from the university that you study, then you should talk to someone from your company or from your university in case you don't have this installed, and try to find a way to install it. Okay. All right. So Meta is a software that we can do many things. Just like ANSA, I'm not going to show everything that we can do in this software. This kind of software is, well, you need to learn little by little for this kind of software. Okay, so over time, you're going to learn more and more about it. The good thing is that we have many tools here that are similar to ANSA. So you see that we have this yellow button, oh sorry, the blue buttons here that are similar to these blue buttons here in ANSA. And also the these buttons here are similar to these ones. And anyways, we have some buttons that are similar. So first of all, you see that we have this tab here, geometry, right? We have three tabs: geometry, results, and curves. In the geometry tab, we have file name, and then we can click on this folder to select a file to open here. The file that we need to open here is the one that contains the definition of the mathematical model. That is, in this case, the .inp file. Okay. We can also open the .odb file in geometry, but we are going to have less information about the model if we do that, because the .odb file does not have all the information that the .inp file has. So if you have the .inp file, then it's recommended to open it here in the geometry tab. I'm going to click here. I'm going to paste the path to the working folder where I have the files. And then I'm going to double click on the .inp file to open it. Now here I have the model opened. To rotate, we are going to use the same command as in ANSA. So hold the Control button, and while holding this button, you can use the left mouse button to rotate like this. You see that the mesh is not visible. I like to see the mesh. So there is this button here, wire, activated. And now if I zoom in, I can see the mesh. You see that Meta is a much more beautiful software. So the background is white, and the visualization is much better than ANSA, because, well, in here we are supposed to take screenshots to put in reports and things like that, create animations and etc. Okay, let me check one thing here. All right. So after inputting the .inp file in the geometry tab, we can select the next tab, results. When I do that, the software automatically identifies the .odb file that is placed in the same working folder, in the same folder that we have the .inp file. So the software automatically selects this .odb file. In your case, if it didn't select, then you should click here and search for the .odb file, double click on it, and then it's going to be opened. Now you see that we have this list of states. And then in here we have you can understand states as increments. Okay, so we have for the first step, the result of the first increment. Actually, this first one is for 0. So this is for the initial condition. And then this second row here, where my mouse is positioned, is for the result of the first increment. You see, time is 1e minus 1, so 0.1. So when we had 10% of connector load applied. Okay, so here we have all the increments of step 1 until this row. And from this row until the end, we have all the increments of step 2. So for step 2, we have many increments. We have 96 in total. You see that we have everything automatically selected, which means that any result that we want to plot is going to be calculated for all these increments. We can do this, and that's what I'm going to do. But if we'd like to, we can select, for example, just the end of step 1, and then scroll down and then hold the Control button and then select the end of step 2. Okay, we can do this. We can just calculate what happens at the end of these steps. But I don't want to do this because I want to create some kind of animation. So I'm going to select 1 and Control A. Or I can select the first one, scroll down, hold the Shift button and select the last one. And then we have everything selected. Okay. Now in this region here, you see that I have these 3 boxes checked, right? So this first one is, if I position the mouse, you see that I have this information, read deformation results. So if I have this checked, I'm going to read, deformation here means nodal displacement. We know that deformation is calculated using nodal displacements, but in this software, it says deformation. I don't really like to think about these as deformation because this is nodal displacement. And with that, deformation is calculated. So if I have this checked, this means that we are going to be able to see how the structure deforms. Now this second option is read scalar results, and this is checked. Scalar results is what we are going to define in this tab here named scalar. Okay. By the way, let's go to this tab. And before, let's go to the deformation, because deformation is related to this one. So you see that in deformation, we can select displacement, but we can also select some other things here. But what I usually select here is just displacement, and this is a magnitude of displacement. We can select here a deformation scale factor, but I don't really usually select the scale factor here. I select it by using another button that I'm going to show shortly. Okay. So let's go to the scalar tab. And then in the scalar tab, we can choose one of the output requests that we have defined in Abaqus, in the .inp file, right? So you see that in here we have the stress components selected, but we have many other options here as well. So you see that we have some things related to contact, and we have displacement, rotational displacement, reaction force and moment. We have this composite results. I don't even know what is this. We have stress components, equivalent plastic strain, which is PEQ, and active yield flag. And then if I select, for example, stress component, I can select in this second field what kind of stress I like to calculate. So I can calculate many stresses. So you see that I can calculate von Mises stress if I want to use von Mises yield criterion. I can calculate Tresca stress if I want to use Tresca yield criterion. I can calculate mean pressure. Let's see. We have the principal stresses here. So major principal is sigma 1. Minor principal is sigma 3. We can calculate maximum shear stress at each material point, normal X, normal Y, and we can calculate many other kinds of stresses. So what happens is, let me open here one. Let me show you guys one slide. Let me get the linear FE course material, and then in here, let's check the equations of elasticity module. And then in here, let me go to the last slide. We have the governing equations for this mathematical model that we have solved, right? We have the stress-strain relations, strain displacement relations, and equilibrium equations. When we solve the mathematical model using the finite element method, or actually Abaqus does that for us, Abaqus calculates the active displacements, right? With the active displacements, which are the nodal displacements that are unknown. So imagine that we have the prescribed displacements. So this is a displacement that is known because we prescribed these displacements, such as the displacements of this node and this node. And we have the unknown displacements, which are named as active displacements, as we have learned previously, right? With these calculated, we can calculate everything else. And that's what meta does. So you see that, for example, I can calculate a strain by using nodal displacements. You see in here, I have the displacement field. We know that displacement field U, V, and W can be calculated using the nodal displacements and the shape functions, right? And then we can calculate a displacement field inside each element, and with that, I can calculate the strain components. In here, we have an example of how we calculate infinitesimal strains. But we know that in this situation, we have finite strains. We have large strains occurring. So then we learned in the 5th module of this course, actually in the 4th module of this course, that we have some other strain tensors that can be also calculated by using the nodal displacements. Okay. So a strain can be calculated using nodal displacements, and then we can calculate the stress by using stress-strain relations. So by having strain, we can calculate stress. Okay. So what we have here is the post-processing of the active displacements. The software is capable of calculating a stress tensor in each location inside the element and also at the boundaries of the element. And with this stress tensor, it can, for example, calculate the von Mises stress in any location. We know that the von Mises stress is calculated using the stress components of the stress tensor, or also by using the principal stresses. The same thing for the Tresca stress. Here we have the stress components of the stress tensor, normal X, normal Y, normal Z, and the shear stresses. And anyways, let's start then calculating von Mises stress, because this is a ductile metal. we are dealing here with ductile metals. So this is an appropriate yield criterion to be used for a ductile metal. Okay, Vomisis and Tresca. We can choose one of these. We know that Vomisis is less conservative, so it yields to well, less conservative calculus, obviously. Now in here, we are dealing with shell element, right? So the shell element is in the mesial surface of the solid entity. So we have half of the thickness above and half of the thickness below, right? In this field, we can choose, well, this can be calculated. We can calculate the maximum in-out layers. This means that what is going to be shown here, let's do one thing. Let's calculate it, and then I'm going to explain. Okay. Actually, let's firstly calculate this option here, inner and outer. And then here we can choose the position that this stress is going to be calculated. Well, this depends on the kind of element that I'm using. In this case, we know that S4 is a fully integrated element. So for example, this rectangular element has 4 integration points, right? So this has 4 integration points. And in this case, I usually calculate the stresses in the integration points. Okay, so I ask the software to calculate these stresses at the integration points. And then the software is going to interpolate in between. So INT, PNT is integration point. We can also calculate on the corners, that is at the nodes, or on the centroid. But on the centroid is not really a good option, because then we would have only one stress being calculated at the centroid of the element. So we would have less stress points being calculated by using these expressions that we have here. Okay, not exactly these expressions, because as I mentioned, here we have finite strain, not infinitesimal strain. So integration point. All right. Here we have some other options. We don't need to change anything here. We can accept the default configurations in this first exercise here. We have this last tab vector, but we are not going to calculate anything related to vector now. So we can even, you see that this option here is read vector results. We can even uncheck this box. So we are going to calculate a scalar results, which is what we have just defined here. And we are going to calculate deformation. Now, if we click on read, the software is going to start calculating the Vomisis stress and the deformation for all the states that we have selected here in the first tab. So you see that in here, in this region of the screen, it's showing the progress of this calculation. Since this model is not so small, and since we have many states, it takes some time to read it, as you are seeing here. Let me show some things that are interesting while this is being read. First of all, if we go to Tools and Settings, and in here, click on, in this, we have Windows Settings, and then Drawing, and then in here, go to Model Geometry, and then a shell solid element, and then draw thick shells. You see, this is not so practical, you know, to go to Settings, Drawing, and then this tab, and then this tab. This is not so practical. What the companies usually do is, well, they create shortcuts for tools that are used frequently. But I'm not doing this in this tutorial, because I want to show you where you can find because you firstly need to learn in this manner, and then you later can create shortcuts. Now you see that we can see the thickness of the shell elements. Okay, this is going to be interesting in this case because since we are asking the software to calculate this in the inner and outer surface, the software is going to calculate a stress on one side of the shell element here and also on the other side. And we are going to see stress variation along the thickness of the shell element. So this is going to, well, it's interesting to keep the thickness apparent here. It's yet reading it. Let me show you another thing that is interesting. You see that we have this bubble. I guess this is a light bubble, right? Left click in here, and then in here we can control the visibility of some entities. So for example, if I don't want to see beam, I can uncheck this. Let me zoom in here. You see that I have the beam here. If I uncheck, I cannot see the beam anymore, but I want to see it. So check it. This is for coupling, but I want to see it. This is for a coordinate system. In this case, we have this coordinate system here. If I uncheck, it's not visible anymore. This one is for surface from solid. This is for the surfaces generated when we established the contacts. I usually don't like to have it visible, but I'm going to have it visible just for you to see it. And then we can uncheck this. This is for kinematic. Oh, sorry. This is for when we have MPCs. In this case, we don't have, so this is not important. And anyways, we can also check this to see boundary conditions and etc. Let me close this. You see that in my case, it has finished reading. Let me deactivate my camera. And now let's see the deformation without plotting anything yet. So you see that we have this region here. We can left click on this thing here, and we can left click and hold and then move it like this. And then you see that in this region of the screen, we have the information about the state that we are. So we are in the bolt pretension step and a 7.3 E-1 increment. So in this case, we have the bolt pretension being applied here in this region. We can see so much. We are going to scale this to see it better shortly. So you see that here we have the end of step 1. And then if we go one additional increment, we are going to have the start of step 2. And then we have the displacement occurring there, you see? And then everything is deforming a lot. And then you see that, let me zoom in this region. Look at what happens here in this region. We have some kind of buckling occurring here. You see? It's deforming a lot because the displacement that we applied is very large. We actually have a lot of buckling occurring here, which is something that is expected. You're going to see in the images of the experimental data that this actually happens in the physical model, which is so nice, you see. It's really nice to create a simulation and compare with experimental data, and also compare to the pictures of the experimental data and see that what we have calculated here actually represents the reality. I don't know, guys. For me, this is really nice. And I'm actually impressed that this analysis has converged until the end. Well, because this is a static analysis, it's usually hard to converge a static analysis, even using good software such as Abaqus. But in this case, it has converged until the end, even having this large deformation occurring. Okay. Look at how we have this part deforming. You're going to see in the experimental pictures experiment pictures, we have the same thing happening. Well, anyways, you can look around the model. There is another thing that I wanted to show. Let's press F1, F2. Yeah, F2. You see that while we have this displacement occurring, since we have just applied this downward displacement without any kind of restriction, we also have this displacement to the right occurring. We could have fixed this displacement in the y direction so that we don't have this happening. And maybe this is a good idea, you know, because in the experiment, we have this kind of restriction. If we look at this image here, where we have the load being applied, this system that applies this load kind of creates this restriction. I don't know how much resistance this creates, but it creates at least a little resistance, or maybe a lot, I don't know. So maybe this is something that we should think about, you know? But anyways, let me think here. Okay, so you can look this model around, and now I'm going to plot stress. So let's do this. You see that we have this button here, right? We have these two buttons. This one that is activated is related to deformation. So for example, if I select this state where we have some deformation, and if I deactivate this option, I cannot see the deformation, even though I have this state selected. Okay, but I want to see this deformation. And if I go to, if I click here, you see that I can select a multiplier. So for example, if I select a multiplier equals 5, so type 5 and press enter, then it's going to amplify this deformation by 5. However, since this deformation is already very large, we don't need to do this. So let's select 1, press enter, and here we have the real deformation or displacement. Now this second option is for to plot the scalar that we have selected here. So if we activate it, now we have stress plotted here. If we click on this drop down list, sorry, not drop down list, you know, this symbol, we can set up some things here. So you see that what we are seeing here is the scalar value that we have selected here, but we can also plot total deformation. So this is not deformation, this is displacement. I don't know why the softwares name this as deformation. What you see this in this scale here is displacement in millimeters. You see, so the maximum displacement in this case is 172. If we go to until the end, we have a maximum displacement equals 224. Let me go back here, and then I can plot displacement in the z direction, y direction, x direction, and etc. But what I want to see is the scalar that we have selected here. Okay. Now, in this part, we can choose between. Let me check if my camera is not activated. Okay. In this part, we can choose between a normal plot or contour plot. We also have these other options, but I'm going to talk only about these two. So here you have normal plot, and this is how it looks like. Now, contour plot looks like this. It creates the contours. The normal plot creates a smoother transition between the scale colors. To be honest, I prefer contour plot. I prefer to see these contours. But you see that if we zoom in, you see that we have this discontinuity occurring between among the elements, right? Guys, let's remember one thing that we have learned in the linear FEA course, and that is very, very important. We know that a defined element method is a numerical procedure to solve a mathematical model of the type boundary value problem, right? And the solution is approximated. We know that in this solution, the displacement field is continuous among the elements. So if I calculate here displacement in this option, click here and then calculate total displacement, you're going to see that we have a continuity between in the element. So we have some continuity here of displacement, which means that if we plot here again scalar and zoom in, you're going to see that we don't have, for example, in here we can see very clearly that we don't have this kind of continuity occurring of stress in this case. And this is something that occurs in the solution of the mathematical model using FEM. Okay, we don't have continuity in the strength field, and obviously in the stress field as well. Okay, we have only continuity in the displacement field. But this discontinuity in the stress and strain field decreases when we have a finer mesh. And in this case, you see that the mesh is considerably refined, so the discontinuity here is not so bad. Well, if we click here, you see that this result is plotted on element, but we can choose on node. If we choose on node and zoom in, you're going to see that it's going to look much better. And what is happening here is that instead of plotting the real stress that we have inside each element, this software is actually calculating the stress for each element. And for example, the stress at this node here, we have this node shared by 4 elements, right? If we calculate the stress at this node, considering these elements, I'm going to get a value. Now, if I use these elements, I'm going to get a different value. And if I use this element, I'm going to get a different value again. Anyways, I'm going to have 3 different stresses calculated for the same node. When we select on node in there, the software is going to get these 4 different stress values, and it's going to calculate the average, and it's going to attribute this average for all elements. So the software is going to calculate an average of stress at this node, this node, and this node. And then after that, it's going to use some kind of interpolation to calculate the stress inside the element. Well, when the software does that, we're going to end up having some continuity because the stress at each node is going to be equal for all elements that are sharing this same node because of this averaging procedure. And then we're going to end up having this more beautiful stress plot. I usually use this, but you should know that if you are working in a big company, if you get to work in a big company, what you're going to need to do is to follow orientations. You're going to have a file with orientations of how you should post-process results. So in this file, you're going to have orientations such as you should calculate stress in the integration points. You should average stress. So you should calculate it in this manner where you have the average at the nodes. Anyways, you're going to have orientations. But if you don't have any orientations, then what I suggest you to do is to choose here on node and contour plot. This is the setup that I use. Okay. All right. Now let's understand then this inner and outer. For example, if I analyze here, let me see if this is a good. Yeah, this is a good position. You see that for this specific element here, right? If we look at the stress on this side, we have this. Now, if we rotate and look at the stress on this side, we have another stress value. And then we have a variation of stress along the thickness, right? Let's see one region that we have more variation. You see that in here we have a lot of variation of stress along the thickness of the element, right? So that's it. When we have inner, out, and outer, the software does that. Now, if I have here max, in, out, all layers, the software is going to calculate the maximum stress, the side that has maximum stress. For example, in this case, it is this side. And then it's going to consider this stress on the other side as well. And this is what I actually select most of the time because I'm interested in calculating the maximum, absolute maximum von Mises stress. That's my interest when I'm performing these analysis and when I want to analyze if I'm having plasticity or things like that. So I don't want to see stress on the other, on both sides. I just want to see the maximum stress. So, for example, if I want to calculate this as well, don't press read. Don't press read here. Because if we press read, we are going to overwrite what we have calculated here. So if we don't want to overwrite this calculation, we should activate this plus button here. So you see, when toggled, a new label will be appended. Otherwise, the current one will be overwritten. So toggle this, and then you can press read. And now it's going to start reading. And while it's reading, let's continue analyzing what we have here. Let me see. 41 minutes. Okay, my goal here in this video is to calculate this curve that we have here. This is my goal for this video. Guys, I'm not going to spend more time showing. This is the introduction that you need to be able to perform simple post-processing here. We're going to also learn now how to plot curves, which is another thing that you should know. Basically, this is the kind of tool that you're going to use here in Meta 90% of the time. Okay. All right. So let's do this. If we go to this new tab, curves, you see that we have three tabs here, right? We have this first one, files list. In this first one, we need to click here and we need to navigate to the working folder where we have the files. And then we need to choose the .odb file. Double click here in the .odb file. And notice that some information appears here. Now we are in the results tab. What we have here is the history output that is registered or saved in the .odb file. Okay, so here we have access to the history output that we have defined here. So here in the first step, we have defined these two history output requests. As you see that we have it here, these two entities. So first of all, you see, I want to calculate nodal. And then you see that in here we can select the step that I want to calculate. In this case, I want to calculate this curve for the second step where we have the displacement applied, right? So I don't want to have both steps selected here. I just want to have the second step selected here. So left click in the second step. And then let's see, we have a measure rotation and we have disp node. In the measure rotation, we're going to obviously calculate rotation. So let's start with this one. So select measure rotation here. And then this is in the entity group. So basically we are selecting that set that we have defined here in ANSA. that is named as measure rotation and that has one single node, which is this node that we have here, right? So here we select the entity, which is this node here. And then in here we can select what we want to calculate. In this case, I have rotational displacement available to calculate, which is what we have requested. In this case, I want to calculate rotation about the y-axis. Okay, so rotation about y-axis is UR2. UR1 is about x, UR2 is about y. So select UR2. And then if I click on read, we have this plot, right? You see that in this region of the screen, we had the MetaPost window, which is this one. And now we have this new one, window 1, which has this curve. Okay? But the problem is that here we have rotational displacement in the y-axis and time in the x-axis. This is not what I want, right? I want rotation versus bending moment. So you see that we have this new tab. I know that meta is a little confusing at first, but you're going to get used over time. In the plot lists tab, we have this curve entity that has been created, right? Now, if I want to plot one additional curve here, I can go back to read results. And then now I want to select this node, which is a set, this one, that has this node where we have the displacement applied. And in this case, I want to calculate the reaction force in the z direction. So you see that in this list we have the available options. And I'm applying a displacement in the z direction, right? And this is going to generate a constraint equation that we can now solve and calculate a reaction force. And that's what is going to happen here. And I want to calculate the reaction force in the z direction because we have the displacement in the z direction, right? So RF3 is reaction force in the z direction. Now click on read. Now let's go to the plot lists tab, and you see that we have these two curves plotted in the same chart, right? But this is not what I need. So what I'm going to do here is I'm going to generate a new curve by using the information of these two curves. How do we do that? We are going to calculate in the calculate menu and curve functions. And then in here, let me erase this information. And then in here, I'm going to select create curve and then user defined. And then in the X, as the X-axis, I want rotation, right? So while you, first of all, double click on this curve, measure rotation, and then you can close this. And now select this field, and then click here, and then go to expressions, and then you see that we have C1X and C1Y. Well, I double clicked on this curve because now we have this curve selected, and then the expressions that appears here is related to this curve, which has ID equals 1. So that's why we have C1. Okay, you see the ID is here where my mouse is positioned. So in the x-axis, I want to put C1.y. Because C1.y is going to contain the information about rotation. Because you see, this curve is rotation in the y-axis versus time in the x-axis. I want the y-axis that has rotation, right? So C1y. In the y-axis of this new curve that I want, that I'm creating, I want bending moment, right? So first of all, select this curve. You don't need to double click actually, you just need to select it here and then click here and then expressions. And then I want C2Y. So I want the data in the y-axis of the curve 2, that is the one that has force. So C2y, right? Now, this is force, right? I want to calculate a bending moment. This is something that is interesting. We know that, well, here in ANSA, if I measure the distance between this point and this face store, we have the x component of this distance equals 1200. Well, we have created this geometry in this manner. And also in here, the person also considered this distance to calculate the bending moment. So if we multiply the force that we have here by this distance, then we are going to have bending moments around the end plate position. Okay, so basically here in Meta, we just need to multiply this by, well, let's see, we have force here in Newton, right? Let's see the units that we need to extract this bending moment. You see that in this plot, we have kilonewton times meter. So I need to consider, I have this force in Newton, so I need to transform this in kilonewton. So I'm going to divide it by 1000. Now we have it in kilonewton. I'm going to put it inside a parenthesis. And now this force in kilonewton should be multiplied by 1.2, which is 1.2 meters. Okay. And then the result here is going to be bending moment in kilonewton times meter. But there is one thing here. While we have this displacement occurring in the downward direction, the distance between this point and this face decreases because we have large displacements. It's the same situation that occurs when for the fishing rod. When we have it bending a lot, the distance between the line of action of the force and the fixation point decreases. And this yields to a nonlinearity due to large displacements. So when we have this constant value being considered here, we are going to actually introduce an error in the calculation when we have large displacements. So we should keep this in mind. Okay, we are introducing an error here. Okay, and by the way, the guy that wrote this article is also probably committing this same error. Let's say that this is not, we are deciding to commit this error. It's important to know what errors we are committing, what are the assumptions that we are taking. This is what matters. The problem is when you don't know what are the assumptions that you are taking. Okay, now we are ready. We can click on apply and a new curve is going to be generated. Let me close these. Let me close these. And then you see that in here we have 3 items, right? We have all these curves plotted in the same plot. And that's why it's not looking good. So what I'm going to do is I'm going to right click on this new curve that we have just defined and I'm going to select show only. Now we have only one curve plotted here, but I don't like this curve because you see that here we have negative rotation and a negative force, actually a bending moment. But you see that in this plot we have positive rotation and positive bending moment. So I'm going to multiply bending moment and rotation by -1 so that we have positive values. In this user-defined, double click, and then in the user-defined formula, we are going to put a minus sign here and a minus sign here. So press enter and press enter. You see, select these and press enter, and then this one minus, and then press enter. Now close this, and here we have the plot that has been generated. You see that we have this kind of instability occurring with negative stiffness. And we don't have these occurring here because probably, well, we have applied a too large displacement. Okay, so we can modify the title of this axis. So for example, if I double click on this axis, you see I position my mouse here and double clicked here. I can go to this first tab and change here to the same M, then kilonewton times millimeter, press enter. And when we do that, we have this modified already. We can modify here the size to 20, for example, and that's it. We can close. Oh, actually, let's double click here again, and let's modify the size of this one as well, 20. Okay, now I can double click on the x-axis, and instead of time, this is not time, this is rotation. So rotation, and this is in red, radians. Increase the size to 20, and also here, and that's all. We can change the title. So you see, double click on the title, and then in here in the text, you can type something such as moment versus rotation plot. I don't know. Press enter. Increase the size to 20. Now, if you'd like to output this chart, you see that we have this button here. Click here, and then we can select a directory for this image to be outputted. What I usually do is I select clipboard, and when I have clipboard selected, if I click here, then I have this image on my Control V. So for example, if I open up PowerPoint, here you have PowerPoint opened and Control V, here you have the image, right? And then you can use this in a report. Obviously that we have more advanced tools such as creating annotations and things like that, but this video is long enough and I'm not going to do this in this case. What I'm going to do here is I'm going to extract this data to put in Excel so that we can merge, actually we can put this image on the Excel. Anyways, you're going to see what you're going to do. We're going to do one thing here to compare this data with this one. Okay, so just follow what I'm going to do. In this item that has this curve, double click on it, and then if we go to this last tab, edit, we have this table with this data, right? Select this, Control A to select everything, and then Control C to copy. And then let's open up an Excel spreadsheet. And then Control V, that data here. Now we can go to, well, my Excel is in Portuguese. I'm sorry about these guys, but I guess the names are very similar. If you go to the second tab that in English is Insert, you have the plot here. I want to create this kind of plot. This one. And then here I have an empty plot. Right click, select data, and then in here add, and then in here as the x-axis, click here to select data, and then select all this data until here. And then click here to confirm, and then erase what you have in the y-axis, select here and select all this data for the y-axis. Then click here and then click on OK and OK. Now we have that same plot here. Select these, right click, format, And then in here, select these and then solid line. And that's it. That's all we need. Also, let's check, guys. The connection that we have modeled is SC2, right? This one. So we have this plot here for the connection SC2, right? This second one. And this is moment versus rotation. This is for total rotation phi. Okay, don't take this other plot because this is for phi s. Okay, so we should take this plot here. I'm going to zoom in here and I'm going to take a screenshot of this plot like this. And I'm going to put it here in Excel. Decrease a little the size. And then, guys, just 1 second because my dog is asking to enter in my room. Okay, I'm sorry. He was crying in the door. All right, now we can continue. Let's adjust the x-axis to be the same as we have here. So we have here 0 until 0.12. In the x-axis, click here, right-click and format axis. Let me see one thing here. Let me deactivate my camera. And then in here, in the format axis, you see I'm going to click on this icon. And then in here we have number. And instead of scientific, I'm going to select number. And 2 decimal places. And then in here, I'm going to change this secondary, this primary, the maximum value is going to be 0.12 per center. All right. And the minimum, and then we have here 0.02, so it's the same as we have here. So this principal grid is 0.02, so it's correct. All right, now for the y-axis, select here, and then the maximum is 400. Let's choose here number, 0 decimal places, just to be equal. Press enter, and then maximum is 400, and the principal grid is 50. Okay. All right. The next thing I want to do is I want to go to this tab and I want to hide the visibility of the grid lines. And I'm going to select this plot, right click and format graphics area. And then in this icon, in this first option, I guess this is in English is filling, I don't know. I'm going to select, oh, it's not here actually. Let me see where we can remove the background. Let me select this image, right click and send back. Oh, now it's correct. So it was here, and here, filling, and then without filling. I don't know actually how this is in English. Now we can do something like this. I'm going to move, let me increase a little the size of this image. I'm going to move this plot like this to match, so that the grids of this plot match with the grid of the plots of the article. You see, I have I'm using this line here as a reference, so we can even zoom in this region. First of all, I have positioned this corner exactly in the same position. And I'm going to zoom in here, and then I'm going to adjust this size until I have this grid matching, this corner positioned here, right? So I'm going to perform some iterations here until it's matching perfectly. Let me zoom in again. Oh, looks like it's matching almost perfectly. It's good enough. Now we can finally compare the results. Yep, we can finally compare the results. Guys, I was thinking here that maybe in the experiment, let me see here the experiment. It's in this image. In this experiment, the person was able to calculate the force that this hydraulic actuator generated, right? And then with this force, the person has multiplied it by 1.2 to calculate bending moment. So in the calculation of the experiment, we also have this assumption that this distance here is not decreasing. Probably. I don't know. I don't have this information here. So probably this is happening as well. So this simplification that we are using for this calculation is probably also being used in the calculation of bending moment in the experimental to extract experimental data. Now, another thing that we can notice here is that, first of all, you see this dashed line is the FEA results that this author has obtained through this model that he created, right? And you see that the line that we have extracted matches perfectly in the linear region, but in the non-linear region, it doesn't really match so perfectly. You see, it doesn't match perfectly. Well, this difference here really depends on how he has set up this model. His model has many differences. First of all, he's using solid elements. We are using shell elements. And so this mesh is not really looking so good, in my opinion. And also, he's using a symmetry condition, so he has only half of the model being considered, which means that he has constrained this model in the y direction. Let's look here at this. So you see y direction. His model is constrained in the y direction. So this his beam, if we go to our beam, let me go back to meta post tab. I'm going to press F2. You see that this beam is displacing to the right, in the right direction. So this is different if compared with his model. And also another thing that we can notice here is that you see that in his case, he doesn't have his this instability occurring. His model keeps increasing the displacement here without any kind of instability. Probably he's not being able to capture this instability because the way he has modeled this with this restriction that is imposed by the symmetry condition. I don't think it's a good idea to use symmetry condition as he has used, because this model in the beginning has, well, in the beginning we can use a symmetry condition, but eventually we cannot use it because we have something happening here that is not symmetric, as you see. Right? So this is another reason why we have this difference. Also use, well, yeah, I guess that's all. So the mesh is not looking so good. You see the elements are too large. And the symmetry condition and the fact that he used solid elements and maybe different boundary conditions. Okay, so that's why we have some differences occurring here. Now, let's compare our calculations, this blue line, with the experimental data. Here we have the test line, this continuous line, right? This experiment was performed until failure. Look at how interesting. Our model has, we have this instability occurring in this point where the physical model fails. When we have this instability, you can think that this is, well, we can say that this is failure because we haven't modeled the hardening phenomenon of the materials. We have considered a simplified material model, a perfectly plastic material model. To be able to actually capture when this model would fail, we would need to model the material with more details, like a true stress versus true strain curve obtained through experiment. But anyways, it's interesting that we have this matching when we have instability occurring and when we have failure occurring in the physical model. But you see that in the beginning, our results is matching with the physical model, but when we have nonlinearities occurring, then our model is not really matching. We have some error here. You see, we have this error here. But at least the maximum bending moment is approximately equal when we have failure occurring at this point here. So we almost reach, actually in our model, we reach 350. Let me delete this so that we are able to see bending moment. Oh, let me actually just move this. Or maybe I can change the color to white. No. Oh, anyways, we have 350 here as the maximum bending moment in this location. Okay, so the results are matching reasonably well. There is some error. The reason for that is because we have some simplifications in the mathematical model, mainly related to the material properties that we have defined. Okay, in my opinion, this difference is mainly because of that, because of the material properties. And also because we don't have all the information about how this was set up. You can try to do some tests in your model to see if you're going to have a line that fits better with this. Okay. All right. Let me go back to meta. And remember that we have calculated one additional stress, right? Let me go back here to MetaPost window, this one, and read results. And then now you see that I have plotted Vomis stress, inner and outer, right? If we go back to the scale results tab and in scalar, we have asked maximum of in out. To access this new calculated, and by the way, I guess I have calculated mistakenly in this centroid, but that's okay. I can access this new calculated results here in this list. So you see that I have this one stress inner and outer, and I have this one which is maximum stress. So I can select these in here. And then if I zoom in, for example, in this region, you see that we have the same stress on this side of the shell and the same stress on the other side. Let's compare. If I select this one, then I have a different level of stress on this side and a different level of stress on this side. Okay, so when I have the maximum, I just get the side that has the maximum and consider this for both sides. You see that we don't have anymore a variation of stress along the thickness. Okay, usually this is what I calculate, and I don't usually visualize the shell thickness. So I go to Tools, Settings, drawing, model geometry, show solid elements, and deactivate this option. And now we have here only the middle surface. Let's see, 1 hour and 15 minutes. Well, I guess that to finish this video, obviously that we can do many things here, but I need to select the most important things to show to you. Let's go to this article that has experimental data, and let's see these images here. Oh well, this image is a good. This image is a good one for us to compare what happens in this part here. You see how this how the end plate is deforming? It is creating a shape that is similar to what we see here. Okay. Well, actually, guys, I have more things to show to you. I wanted to show here this region of the beam, what happens when we had pretension being applied. I wanted to show more things. Okay, so I don't want to rush to show these things to you. It's just a few things that I wanted to show in this post-processing. And in the next video, I'm going to then do it. And we are going to already start the creation of the second model. Actually, we are going to modify this one. We are going to create the solid bolts and solid washer nut, define contact, and etc. Okay, so we're going to modify the model. Okay, we're going to do this in the next video and also finish this post-processing. And by the way, there is one thing that is really important that we should do, which is to verify if we have solved the mathematical model correctly. So we need to, for example, verify if we have equilibrium in this structure. So verify if sum of all forces in all directions is equal to 0. I can't forget to do this in the next video. And this is part of the post-processing. Okay, anyways, I hope you liked it and see you in the next video.